welcome to this lecture 8 of this module 3. This is the last lecture for this module where we are discussing about random variable, their properties and some standard distribution for continuous random variables as well as discrete random variables. So, up to the last class we discussed some of the continuous random variable, and we discussed that there are few more is pending, but still whatever is covered and whatever will be covered in this lecture may not be the full list of the standard probability distribution. There could be some other as well, but these are the distribution which are mostly used for different problems in civil engineering. So, in the last class there is the Weibull distribution was pending. So, we will start with the distribution this class, and we will also discuss some of the distribution after that we mentioned in the last class, that chi-square distribution, T distribution and F distribution, which are mainly used for the different statistical test. So, our this lecture on that probability distributions of continuous random variable will continue in this lecture as well, and we will discuss Weibull distribution first and then some of the distributions which are specifically important for the different statistical tests, and the this statistical test will be carried out in the last module, module 7, where the properties of this distribution, particularly these three distribution, that chi-square distribution, the students T distribution and F distribution, will be used for different statistical test that we will discuss. In this lecture, we will just discuss about their basic properties and which distribution is suitable for what type of test, that we will discuss in this class. So, we will start with this Weibull distribution. This general form of the PDF of Weibull distribution looks like this. There is two parameters, one is beta and another one is lambda. So, this PDF probability density function is beta by lambda, x by lambda power beta minus 1 exponential minus x by lambda power beta for x greater than equal to 0. So, for this support of this distribution is bounded at 0. So, lower bound is 0 and upper bound is infinity, and for the negative values of x, this is not defined, this is 0. And we know that the cumulative distribution for any PDF is the integration from this lower support, that is here is 0 up to here is 0 up to that particular value x. If we do that integration, we get the cumulative distribution function, and this can be shown that this is 1 minus e power minus x by lambda power beta for x greater than equal to 0. So, if we compare this distribution from the whatever the distribution we have discussed earlier, then we will see that we discussed earlier the exponential distribution, we discussed earlier that gamma distribution, and this particular distribution is having some kind of sense of generalization of those distributions, and we will show that how this distribution is related to those distributions as well, that is exponential distribution and gamma distribution. So, the other properties of this distribution is first this is one example of that Weibull distribution PDF, how the PDF look like. Here the the parameters that is taken as this lambda equals to 1 and beta equals to 2. So, taking this set of parameter, this is the general shape of this one, which we can see that this is a positively skewed distribution and lower bound is 0 and upper bound this is coming and asymptotic to 0. So, this is your x and this is your fx, that is density of probability. And for the same combination of the parameters, that is lambda equals to 1 and beta equals to 2, that is the same PDF that is shown in the last slide. If we take that cumulative distribution, that is fx, is capital Fx x, then we will get this type of distribution, which is starting from 0 and asymptotic to 1, like this type of distribution we can see. So, now this first few moments, if we discuss about this one, that this mean is given by mu equals to lambda, this is one parameter, and this gamma function of 1 plus beta inverse, that is 1 plus 1 by beta. We discuss about this gamma function some previous lectures while discussing that beta distribution and gamma distribution. So, if we know the value of this beta, we will be able to know what is the value of this gamma function, and we will be able to calculate this mu. So, this mu is dependent on both this parameter we have seen, and similarly the variance also is given by this expression, which is lambda square multiplied by gamma of 1 plus 2 beta inverse and minus gamma square 1 plus beta inverse. Basically, this one, if we just this lambda square, if we take inside this bracket, this becomes that mean. So, that mean square. So, we can say that this quantity, that is the lambda square multiplied by gamma 1 plus 2 beta inverse minus mu square will be the variance of this distribution. And similarly, if we take that skewness, we will get a long expressions like this, which is the measure of the skewness of the Weibull distribution. One thing is important here, that if we discuss that if we simply put that beta equals to 1 here, then you know that this will become that gamma 1 plus beta inverse. So, what we are trying to say here, if we just put that beta equals to 1, then that mu, that lambda gamma 1 plus beta inverse, which is equals to lambda gamma 1 plus 1 lambda gamma 2. So, and from the earlier lectures, we know this gamma, if this one is one integer, then we know that this, if gamma n equals to n minus 1 gamma n minus 1. So, this is 1 gamma 1, and this gamma 1 value is equals to 1. So, this is basically 1. So, this expression, that is mu, becomes lambda. Similarly, if I take that sigma square, which is the expression is this lambda square multiplied by gamma 1 plus 2 beta inverse minus gamma square 1 plus beta inverse. So, putting this beta equals to 1, it will eventually come that lambda square gamma, this is 3 minus gamma square 2. So, this is 1 and this will become your 2. So, lambda square, this is 2. So, gamma 3, you know, gamma 3 equals to 2 gamma 2 and gamma 2 equals to 1. So, it is 2 minus 1 square. So, this is equals to lambda square. Now, if we see that for the exponential distribution, we got exactly the same value of these moments, at least the first two moments, that is for a exponential distribution, that mean is equals to lambda and variance is equals to lambda square. So, if we put this beta equals to 1, it seems that it is becoming an exponential distribution. So, if we just go back to the to this distribution of this Weibull PDF, and here if we put that beta equals to 1, then we can see that it is 1 by lambda, and here it is beta equals to 1. So, this is 1, and this e power minus x by lambda for x greater than 0, and otherwise it is 0. So, which is nothing but exactly same to this exponential distribution. So, here, so with respect to the exponential distribution, we can say that one more parameter is introduced, which is beta. If this beta is equals to 1, this Weibull distribution becomes exponential distribution. And we will also show that how this Weibull distribution is also that gamma distribution is a special case for this Weibull distribution, that we will discuss in a minute. So, now this we discuss, and this first few moments, mean, variance and coefficient of skewness we discuss. some note that what just now we discussed is the first note, that when the parameter beta equals to 1, the Weibull distribution becomes an exponential distribution, which just now we discussed. Now, if we just want to see the effect of the parameters, that is both for this lambda and beta. So, if we just keep one parameter constant and if we just increase the other parameter, then what will be the effect on the safe of this PDF of Weibull distribution. So, the first it says that for a constant value of lambda. So, if we just take a constant value of lambda and if we increase this beta, so as beta increases, the skewness decreases and the Weibull distribution becomes almost symmetrical. So, this is important in the sense that when we need to model some random variable which is symmetrical as well as this is lower bounded by 0, then we can say that okay, this Weibull distribution may be a suitable choice for that case, because we can estimate this beta is high and then this Weibull distribution becomes symmetrical. That we will see that how it is changing based on the different values of this beta. On the other hand, if we take this beta as constant, if we take some constant value of beta and if we increase this lambda, then the peak lowers and the Weibull distribution becomes more flatter. So, Weibull distribution becomes more flatter means that its peakedness reduces, its skewness also reduces, it becomes more flatter. So, if we see that it's safe depending on this different combination of this parameter, that is alpha and beta, then this will be more clear to us. So, this is the first thing, that when we are keeping this lambda constant and varying this beta, and beta equals to 1, 2 and 4, and keeping the in all three cases this lambda is equals to 1. What you can see here, that this for this blue line, this PDF shown by this blue line, this is for the combination that lambda equals to 1 and beta equals to 1. For this black one, the combination is the lambda equals to 1 and beta is equals to 2, and for this green one, this lambda equals to 1 means all the lambdas are same for all three, and beta equals to 4. So, from this blue, then black, then green, the beta is increasing from 1, 2 and then 4. So, here two things we can see. The first is that just now we discussed that if beta is equals to 1, when we say that beta is equals to 1, that means we are talking that irrespective of any value of lambda. So, when beta is equals to 1, it approaches to the exponential distribution. So, that we can see here that this is an exponential distribution, and we know that this at 0, at x equals to 0, the value of fx is 1 by lambda. So, as we are taking the lambda equals to 1, that is why that x equals to 0, it is coming to be 1. Similarly, now when we are increasing this beta from 1, 2 and 4, we can see that this is becoming some this is again, these are positively skewed. We know the exponential distribution is positively skewed. This can be seen graphically as well as mathematically also, we have discussed in previous lectures. Now, when we increase beta from beta equals to 1 to 2, the skewness asymmetry decreases. So, it approaching to the symmetrical, and it is more clear when we are going to this 4, that it is becoming somewhat more symmetrical compared to the other two graphs where beta equals to 1 and beta equals to 2. So, if we further increase beta, we can see that it is becoming more symmetrical with respect to its mean. Mathematically also this can be shown, that we will see in a minute. Second case, if we just keep this beta constant and if we change the value of lambda, here we have shown these three different PDFs with different combination of lambda and beta. So, this first one, this blue one, is for this lambda equals to 1, beta equals to 2. This black one is the lambda equals to 2, beta equals to 2, and this green one is for lambda equals to 3 and beta equals to 3. Thus, for all 3 PDFs here, the beta is same, which is equals to 2, and for the lambda is increasing from 1, then for the black it is 2, and for green it is 3. So, what we can see is that when this lambda is low, then its peak is more, and with the increase of this lambda, this peak becomes flatter. Basically, when we are having some set of data, there are some tests to understand that which distribution it is following, and after we select a particular distribution, we generally discuss that we generally want to know what is its parameter. Then these parameters are estimated from the sample data that is available to us. That is basically the first step for any probability model, whatever the problem is faced. So, the sample data is collected. From the sample data, first we test that which distribution it is following, and then we estimate the parameter. So, that while estimating the parameter, there are different methods are available. So, here what we are discussing, that the effect of this parameter, the graphical significance of this parameter, if we select one parameter, if we change one parameter, how the shape and the location of the particular PDF changes. That is what we are discussing for all the models, all the probability distributions. Now, one important discussion with respect to this Weibull distribution is the parameter beta. This parameter beta is playing a vital role, and it is having different meaning for the different ranges of this parameter. First, when the Weibull distribution is used to model the failure time in a system, the shape parameter beta has the following interpretation. So, how this beta we can interpret for the different values or the different ranges of this parameter beta. So, first if we start with this beta equals to 1, that is when we say that beta equals to 1, we know that this is approaching to this exponential distribution. Now, the failure of a system, that means that we know that value is constant, that is that failure rate. If we while discussing that exponential distribution, we discussed that the failure rate or the interarrival rate, average time on which a particular phenomenon is occurring, that is constant over time. Based on that assumption, we develop that exponential distribution. This is exactly what is stated here, that is, if beta equals to 1, it indicates that the system has a constant failure rate. That means, which is the basic assumption of the exponential distribution, and we have also discussed that when beta equals to 1, the distribution is approaching to the exponential distribution. Now, there are two other reasons. If beta is less than 1 or if beta is greater than 1, what does it implies? So, when we say that this beta is less than 1, it indicates that the failure rate is increasing with time. That is, a tendency to fail is increasing with the aging of the system. This is important for different civil engineering problem. For any structure that we take, due to its aging problem or some apparatus for its fatigue problem, when the time increases, sometimes the interarrival rate of the phenomenon may increase. So, here we are deviating from the basic assumption of this exponential distribution, that this rate of this failure need not be constant over the time starting from 0 to the any positive infinite towards the plus infinity direction. So, when we say that this rate of failure is increasing with time, that means that is captured when the distribution is having the parameter that beta is greater than 1. Similarly, so this is, you know, that when some particular structural member or the structure itself, due to its aging problem, when it is passing more time, the chances of failure is increases. So that kind of cases, what happens, this Weibull distribution with beta greater than 1 will be a suitable case. On the other hand, when the beta is less than 1, it indicates that the failure rate is high initially and decreases gradually as the defective elements are removed from the population. Now, rather to come to this civil engineering problem, if we just take a social problem, then it will be more clear that if we say that due to the health condition, this is a health system, if the mortality of the babies is increased at birth, then this is one of this very suitable application to model that kind of situation with this beta less than equals to 1. So at the birth itself, the mortality rate is more compared to when the age increases of this of the child. Similarly, for if we come to this some application of the civil engineering, that time when we are producing some kind of product and we are just marketing it. Now, if there is any defective element in the population, then what happens, and if there is any the initial check of this whatever the product is developed, then there is a chance that if we can separate out those defective materials, then that can either fail at the initial stage itself, or if it pass from this initial stage, then it can go for a long time. So what I am trying to communicate is that this rate of failure to the initial time step is more compared to that when t increases. So at that case, that beta is less than 1, so that the failure rate is high initially and decreases gradually as time pass. So these are the interpretation of this parameter beta for a Weibull distribution, and suitably we can think of that for what kind of situation, which range of beta is suitable for different problems in hand. These examples of the Weibull distribution in civil engineering, as we discussed, that this Weibull distribution is often used to study the failure strength of engineering materials and also to describe the failure time of the machine. So it can be, so the failure time of a machine or the failure strength of the engineering material, if I assume to be constant, then it can be as well an exponential distribution, that means Weibull distribution with parameter beta equals to 1, or it depends on that what kind of situation, what kind of problem in hand, based on that the beta parameters may change. Secondly, sometimes the probability distribution of the wind speed, particularly the hourly wind speed, is also has seen to follow the Weibull distribution. So that is also designed using the Weibull distribution. In the application of water resource and hydrology, the annual maximum daily rainfall depth, if I take, and that data also has found to follow a Weibull distribution with suitable combination of its parameter lambda and beta. Next, we will discuss three distribution one after another. We will start with the chi-square distribution, and these distributions are mostly, as I mentioned earlier, these distributions are mainly important for the statistical test, and different types of test is carried out using different types of distributions. So first we are discussing this chi-square distribution, which is generally used for the purpose of goodness of fit. So many times I have mentioned that once the sample data is available to us, we generally have to test that which distribution it is following, and so this is also can be tested statistically, and that test is generally done through this chi-square test, it's called, and based on this chi-square distribution. So we will understand now what are these distribution and what are their different properties. So first we are starting with this chi-square distribution. If Zi equals to 1 to n, that is Z1, Z2, Z3 up to Zn, are independent and identically distributed. Of course, we use the word these three word together, the independent and identically distributed. Sometimes it is abbreviated as IID. Here these are independent of course and following the standard normal distribution, that means these are identically distributed. So, independent, standard, normal, random variables, then their sum of the squares. So, this is important, that square, the sum of the squares of these n random variables that follow a chi-square distribution with n degrees of freedom. So, here that x, that the random variable that I am defining is equals to the summation of those z1 square plus z2 square plus up to zn square. So, where this z are the standard normal distribution. So, if I say that okay, this y is following a normal distribution with mu and sigma their parameter, then we can make it, we can get their reduced variate z, which is equals to y minus mu by sigma, and this z for these n numbers of independent random variables are there. If we square them off, add them, then this random variable, that summation x, that is follow a chi-square distribution. Now, the PDF of this chi-square distribution is like this, that is this is f chi-square x is x power nu minus 2 by 2 divided by 2 power nu by 2 gamma nu by 2 exponential minus x by 2 for x greater than equals to 0. Here nu is the parameter known as the degrees of freedom. This is an integer, this is a positive integer, and this distribution is again lower bound by 0, and for the negative values it is 0. So, this nu here mentioned that this nu is a positive integer known as degree of freedom. Again we know that from this distribution, this cumulative distribution is nothing but the integration from the lower support to a specific value x of the PDF, and this is also defined for this x greater than equal to 0 and 0 elsewhere. So, we will know that its different moments and different initial moments. Now, before that we will show the how this for this different values of this nu, which is that the degrees of freedom for this chi-square distribution is this. So, here we have used different combination of this nu, and we are showing that as this nu increases, then this is becoming this. So, this blue is for the maximum values of nu compared to this green and this red here. So, this is if the degrees of freedom increases, is generally become more symmetrical. And for the and these are the for those three chi-square distribution, these are the cumulative distribution for those PDF that is shown in this last slide. Now, the initial few moments if we see, then there are some interpretation, particularly its skewness, as just we have seen from this graph. The first is this, its mean. The mean of this chi-square distribution is equals to its degree of freedom, which is nu. The variance of the chi-square distribution is 2 nu, that is double of the mean, and the coefficient of skewness if we see, then this is that 2 by square root nu by 2. So, the square root nu by 2, so this is always positive. So, the chi-square distribution always a positively skewed distribution, and you can see here what we have seen graphically in a minute back also, that if we increase this nu, that is if the degree of freedom is increased, then this becomes lower and lower, and for a very high degree of freedom this becomes almost symmetrical, as this skewness is reducing with the increase of this nu. So this is again explained here graphically, that is when the degree of freedom of a chi-square distribution increases, the skewness and the peak reduces and is approaches to a normal distribution, in the sense that it is approaching to a symmetrical distribution and going away from its origin. Here we have taken the 4 examples with different values of degree of freedom. So the first one, the blue one that you see, that is for the degrees of freedom, that is nu equals to 5. The black one, that nu equals to 10. Then this green one is 20 and this nu is 35. So here we can see that as this degrees of freedom is increasing, this distribution becomes almost symmetrical. Of course, all these distributions are lower bounded by 0, that is the basic property of this chi-square distribution. But as this one increases, this approaches to a approximate normal distribution with very high value of these degrees of freedom. Now this chi-square distribution is a special case of the gamma distribution with beta equals to 2 and this alpha as the half of the degree of freedom. So this is, there are 2 graphs as shown, is that this is the this, if we say this is the chi-square distribution with nu, that is the nu, the parameter of this chi-square distribution is equals to 5. So if we take this one, that nu equals to 5, then the shape look like this, that PDF shape look like this. Now if we, this is a gamma distribution with 2 parameters, we know that this gamma distribution is having 2 parameters. The first, that beta is 2 and the alpha is equals to half of the this degrees of freedom, that is 2.5. So if we plot a gamma distribution with alpha equals to 2.5 and beta equals to 2, then we get exactly the same PDF with for which is for the chi-square distribution with degrees of freedom 5. So this is the relation between this chi-square distribution and the gamma distribution. Now if that xi be a series of independent chi-square distribution, chi-square distributed random variables with parameter nu I, that is for first that x1, this degrees of freedom, that the parameter is nu 1, x2 parameter is nu 2, then their sum, if I take the sum of those all those xi's, that is from 1 to n, then a new random we will get a new random variable x, which is a summation of them, simple arithmetic summation. Then this new random variable is also a chi-square distribution with the parameter is equals to summation of all those degrees of freedom. So this is the additive rule, you can say, for this chi-square distribution, that is if we add more than one chi-square distribution and if we know there what is the degrees of freedom, then we can get a new random variable which is also chi-square distribution, and degree of freedom for this new random variable is equals to the summation of the degrees of freedom for all those random variables which we added up. So that is explained here for this first note of this chi-square distribution. The second is that if a number of random variables, that is x1, x2, xn are independent and identically distributed random variables with normal distribution with the parameters mu and variance sigma square, mean mu and variance sigma square, then the random variable, if we take here, that is xi minus x bar square, then sum them up. This variable, this is also a random variable which will follow a chi-square distribution with parameter that nu is equals to n minus 1. Now there are 2 things here. The first one is that we have n random variable, all are random, all are normal distribution, that is identical distribution which is normal distribution with their parameters. Now if we if we get the another parameter, we know that if we just make them square, this is what we started the discussion of our chi-square distribution earlier. But here what we are doing is that we are instead of calling this random variable to be the standard normal distribution, we are just making it general, that is these are the normal distribution with some parameter of mean and variance. Then if we add them up after deducting their mean, this x bar is the sample mean. So, this x bar is equals to summation of all these their values divided by the n. So, that is that average of, that is a mean, that is a sample estimate of the mean. So, if we take out that mean and then square them up and then add them up, then we will also get one new random variable which is obviously follow the chi-square distribution. But earlier we told that this follow a chi-square distribution with parameter that nu equals to n, because we are adding n degrees of freedom, but here the degrees of freedom is that n minus 1. So, this 1 degrees of freedom is lost, and this loss of this degrees of freedom is due to the calculation of their mean, because I have to calculate their mean from the sample, that I have to deduct from them to and then square it up. So, while calculating this mean, the 1 degrees of freedom is lost, and that is why this degrees of freedom for this random variable which is chi-square distribution, this degrees of freedom is n minus 1. Another random variable, if I take that this s is now the sample estimate of the standard deviation. So, this s square divided by this sigma square. Sigma square is this population variance of this population. So, this ratio multiplied by the n minus 1. So, this is also, this total quantity is also one random variable which is also a chi-square distribution with parameter nu equals to n minus 1 with this degrees of freedom n minus 1. So, this one is basically these two properties why I am stressing is that these two are the basic properties which is generally used for the different problems. The first one is that when we just take the difference from a particular value, take the difference, square them and add them up. So, this property is generally used to test the goodness of fit. So, when we take a sample data and we take that what is the distance from the target distribution. Suppose that I have a sample distribution and I can calculate their empirical cumulative distribution, and for some known standard probability distribution, say for example the gamma distribution, for that gamma distribution with some set of parameter I know how the CDF looks like. So, what I can do is that from the sample data the calculated CDF, and for a standard distribution, that is in this case what I am discussing is gamma. So, that if we take the gamma distribution, then what we can do for each point of the sample, I can calculate what is the distance of the two cumulative distribution function, and that distance if I just square them up, add them up, and obviously then you can see from this discussion that that particular random variable will follow a chi-square distribution. So, generally for the goodness of fit test, that is why we use the chi-square test. Secondly, the another application is that for this a square. So, when this a square, that means the sample estimate of the variance. So, for that is also follow a chi-square distribution. So, if we need to know some properties of the sample estimate of the variance, then also we can follow this distribution to have some statistical test. This will be discussed in more detail for this module 7 while we are using make use of this chi-square distribution, and of course the other distribution as well which I am going to discuss now. Well, so first of all I want to attract you to this one, the use of the title of this slide, that use of chi-square distribution in civil engineering. So, so far mostly for this all this distribution we have used this word, that use of that particular distribution in civil engineering, but here I just draw your attention because that this use of this chi-square distribution is need not be for this civil engineering only, this is more general and this can be used for any particular application, because these applications are more general in nature, and this is the civil engineering is also not violated. So, even though I mention it here that in civil engineering, but this is in general for all the problems in hand. So, these two are we have just now we discussed that goodness of fit test for a sample data, that need not be only the civil engineering problem data, that can be any data, that is why I just mentioned that one, that is the general concept of this goodness of fit test. And again the statistical test for the sample variance, which also we discussed in this last slide. The next another important distribution is the student T distribution. If y is a random variable following the standard normal distribution and u is a random variable following the chi-square distribution with new degrees of freedom, then if we get another random variable like this, that is y by the square root of this chi-square distribution normalized by its degrees of freedom, that is u by nu whole square root, then we will get this quantity which is another random variable, and this has been found to follow a student T distribution. This is known as T distribution or student T distribution with the degrees of freedom equals to nu. So, its distribution form looks like this, that PDF of this T distribution is given by this form, that is gamma of nu plus 1 divided by 2 divided by gamma nu by 2. This is the normalizing constant to make sure that total area under this PDF is equals to 1, multiplied by 1 by square root pi nu multiplied by 1 plus x square by nu power nu plus 1 by 2, and its support here is minus infinity to plus infinity, which is here that so there is no bound of this support. This is the entire real axis. Over the entire real axis this random variable can take. So, this nu again is the positive integer, which is the degree of freedom for this distribution. And to get this cumulative distribution, again it is that from this left hand support, there is minus infinity in this case to the specific value x, this integration will give you the cumulative distribution of this PDF. These are generally done numerically, because the closed form of this integration is not available. Now, again here we have shown different examples of this different values of this nu, and you can see that here what we can see is that if we increase the value of this nu, this increases, peak is increases with the increase of this degrees of freedom, and it can be shown that for the high value of this nu, high value of this degrees of freedom, it becomes exactly similar to the normal distribution again. So, it will go and approach to this normal distribution with the increase of degrees of freedom. That is what is shown here. And for the for those combinations of this degrees of freedom, here we have shown that their distribution of this CDF, that cumulative distribution of the student T distribution for different combination of that degrees of freedom. Here the red is the lowest, then green, and then the highest is the blue, with so far as this degrees of freedom is concerned. Now, these are again the first few moments of this distribution. The first of all, the mean of the students T distribution is equals to 0 when we are talking about the standard T distribution, because this is the standard T distribution when we say So that is basically is being used when we do this statistical test, and for the standard student distribution, this you know that mean is 0, similar to the fact that for the standard normal distribution this mean is equals to 0. For this variance of this distribution is equals to is related to its degrees of freedom, that is nu by nu minus 2, and this is for when this nu is greater than 2, the degrees of freedom greater than 2, otherwise it is undefined. So you can see that this is a this is again so this as this nu increases, so this is also become this variance is related when this v is greater than 0, then you can see that we are having a positive variance. So obviously the variance is always positive. So that is why when we are taking this this for v less than 2, you know that, so that is why this variance for the student t distribution for nu less than 2 is undefined. And skewness is 0, we know that, we have seen that nature of this PDF. So this skewness is 0 as this distribution is symmetric, and the skewness coefficient if we just see, then this is generally defined for this nu greater than 3, that is the degree of freedom greater than 3. We can say that this this distribution is the skewness is 0. So here if we see that this t distribution approaches to a standard normal distribution as the value of the parameter nu increases. In the figure it is seen that as nu increases, the spread of the distribution decreases and restrict within this plus minus 3 to similar to a standard normal distribution. This is what we are just discussing while giving this example of this, the effect of these different values of this nu. Here also there are 3 plots are shown. The first, this blue one is for the lowest nu. Here in this case, this nu is equals to 1 in this one, in this case for this blue line, and then if we increase that nu, that is for this red one, you can see that it is nu equals to 10, and for this green it is n is a very high value is taken and shown that. So it will mostly, so it is not that it will go on in increasing, but it is asymptotically with respect to this degrees of freedom, it is asymptotically approaching to a standard normal distribution. This is basically used in the case of the statistical test, when you know that any sample data that is having some finite values of sample data. Now when we generally see that this data set is, the number of data points are less, then even though we know that that particular statistics follow a normal distribution, we generally go for this t distribution, because for this t distribution the degrees of freedom is defined here, and we know that for the small number of this sample size, instead of using that standard normal distribution, we use the student t distribution, which is more logical in this case, because for the standard normal distribution effectively the sample size should be infinity. So use of student t distribution, again I am discussing it with respect to the civil engineering, but these application of all these 3 distributions, student t distribution, chi-square and F distribution, are more general in nature. The practical use of student t distribution lies in the hypothesis test of this sample, particularly for the sample's mean. So 2 samples are available to us, and if we have the 2 different mean, then the target is whether we have to estimate that whether which mean is more and which mean is less. So if that kind of thing, that I cannot simply calculate the sample mean and say that this is more and this is less, but we have to test it statistically, in the sense that that whether that's with the some statistical significance level, whether the one mean is really larger than others or not. So one example from the civil engineering application we can take in case of this admixture in the concrete. sometimes we mix some admixtures to a concrete mix and claim the strength has increased. So in that kind of test, what we have to do is that we have to do the two different batches of this concrete cube. In one batch that admixture will be added and other batch without that particular admixtures. Then we have to take that sample, we have to calculate that sample mean, and then if we want to test that which mean is more, whether that is that there is any effect of this mixing this admixture or not, then that we have to test it, that hypothesis we have to test. And while testing this kind of hypothesis where the mean is involved, then we have to follow the student T distribution. This is what is explained here, that let us consider two batches A and B of the concrete cube, where the batch B has been prepared with the concrete containing a special admixture which is expected to increase its strength. If the mean strength of the sample in the batch B is higher than those in the batch A, the student T test has to be performed before concluding that the admixture generally produce a positive effect or not. So it is not only for this one. So wherever we can say that there is that mean is involved, the sample mean is involved, we use this student T distribution. The last one in this series is the F distribution. If the U and V are independent chi-square distributed with m and n degrees of freedom, then their ratio, that is U by m and V by n, will get a new random variable which is F distributed, and for the F distribution there are 2 degrees of freedom, and here so that is gamma 1 and gamma 2 as denoted is here. The gamma 1 equals to m and gamma 2 equals to n. Here the F is sometimes called as the variance ratio, and this gamma 1 equals to m and gamma 2 equals to n are called the numerator and denominator degrees of freedom respectively. So this is the general form of this PDF of the F distribution, that is gamma nu 1 plus nu 2 by 2 divided by gamma nu 1 by 2 gamma nu 2 by 2 nu 1 by nu 2 power nu 1 by 2. This is the normalizing constant, multiplied by x power nu 1 minus 2 by 2 1 plus nu 1 by nu 2 into x power nu 1 plus nu 2 by 2, and this is for this x greater than equals to 0, and otherwise it is 0. And its cumulative distribution, again the closed form is not available, I have to go for some numerical integration. Now this is the effect of these different values of this combination of 2 degrees of freedom, one is the nu 1 and nu 2. We can see that this red, blue and green different combinations are shown here for different set of combination of degrees of freedom, and their respective cumulative distribution functions are shown here, which is starting obviously from 1 and it is asymptotic to 1, starting from 0 going and asymptotic to 1. The mean of this F distribution is the this nu 1 by nu 2 minus 2 for nu 2 greater than 2, and this variance is defined by this nu 1 square multiplied by nu 1 plus 2 divided by nu 1 into nu 2 minus 2 multiplied by nu 2 minus 4 for nu 2 greater than 4. This use of F distribution here in civil engineering, and mostly it is for this general case, when now for this T distribution we told that when the mean of the sample is involved, that time we use the T distribution. Similarly, and when the sample variance is involved, we have used this chi-square distribution. Now suppose that there are 2 samples are available and the ratio of the sample variance from the 2 samples are concerned, then that ratio, to test that ratio we have to follow that F distribution. Suppose that one sample is having one standard deviation is there which is estimated from the sample data, and similarly for the other one. Now if we take the ratio and if we want to test which one is more, then that means that ratio should be either greater than 1 or less than 1 or equal to 1. So, if it is equal to 1, then both the sample standard deviation is same, and if it is more, depending on which one is more and less, that can be decided. So, for the ratio of the variances from two population, follow a F distribution. Keeping that in mind, we can just see where this will be effective. The practical use of F distribution lies in the statistical test of the variance of two samples. Let us consider that N1 and N2 number of tests are performed by two separate methods of this analysis of a constituent in an effluent. If the two methods yield different values of this variance, the F distribution may be used to decide which method is more precise at 1% or 5% level of significance. So, this level of significance and which one is standard will be discussed in more detail in the subsequent module, and that last module, module 7, when we discuss about the statistical test. And in civil engineering especially, you can also say that let us consider that the distribution of the rainfall depth received by two catchments are there. If the mean depth is equal for these two catchments, but the variance differs, then the F test can be used to test the ratio of the variances and conclude whether the variation of the rainfall depth is statistically equal or not. If not, then which one is having the more variation. So, with this I mention once again that this may not be the complete list of all these standard probability distributions, but these are the mostly used in to address the different problems in civil engineering. Thank you.